So, we continue our lecture on process technological operating practice. In that sequence, we will be discussing today foaming slag practice. As I have already explained what is a foaming slag and how does it form in our lecture on slag making fundamentals. Now, the advantages of foaming slag practice are, for example, heat transfer to the bath, is enhanced. How is it enhanced? Because now the arc will be submerged into the slag, and on account of submergence of the arc into the slag, more heat will be transferred to the bath and less heat will be radiated to the wall. Another advantage of foaming slag practice is the foaming slag, it shields metal from atmospheric oxidation. Now, this is obvious, as the liquid metal is shielded by a foaming slag. So, no atmospheric air will come into contact with the hot metal. Third advantage is that it shields arc from exposure to the lining. Now, you can imagine, in the absence of a foaming slag, the arc which is created by striking graphite electrode with the scrap, the arc will be radiating its heat directly to the wall. Now, if we submerge the arc into the foaming slag, what will happen? Then the heat will not be radiated to the lining of the wall, and hence the lining life will also improve. Now, the question is, how does slag foam? How does slag foam? For foaming of the slag, as already I have said, a gas forming reaction during the operation of the electric arc furnace should be there. So, the principal gas forming reaction is again the oxidation of carbon. Carbon plus oxygen, it forms carbon monoxide, or carbon plus FeO in the slag, it forms CO plus iron. So, the gas forming reaction is FeO plus C, that is equal to Fe plus CO, or C plus O, that is equal to CO. These are the gas forming reactions. These are the gas forming reactions in carbon steel making. In case of alloy and stainless steel making, the foaming slag mechanism is slightly different. We will deal at the time when I will tell you the stainless steel making practice. During the meltdown period, progressive melting of the scrap, it exposes arc to the lining of the side wall of the furnace. Now, for the foaming slag, it is required that carbon content of the bath should be sufficient and oxygen should also be available. So, that means for foaming to occur, during the operation, what is required? One required FeO content of slag, then slag should have viscosity. I will not say low viscosity, I will not say also high viscosity, but that viscosity which allows the entrapment of the carbon monoxide bubble. Temperature, and above all, the most important thing is availability of carbon. availability of carbon. Now, why have I written this thing? Imagine, for example, 100% scrap melting practice, hardly there is carbon over there. So, it is not possible to form a practice which runs on 100% scrap. What to do? Then you have to inject carbon if you want a slag forming practice. Also you have to inject oxygen also. If there is a proportion of sponge iron or a hot metal, then carbon content of the bath is available, and accordingly the carbon monoxide reaction will be there. So, what I wanted to say is that the availability of carbon has to be ensured. Now, typically the carbon injection is done around 2.5 to 5 kg per ton of steel is needed. Per ton of steel is required for adequate foaming during the operation. If there are high powered furnaces, they will be requiring around 5 to 10 kg of carbon per ton of steel would be adequate for slag to foaming. Now, obviously, radiation from the arc has decreased, more heat will be transferred to the bath because of the foamy slag practice, or the arc is submerged into the foamy slag. The electrical efficiency will be high, and accordingly the power consumption will be low. Now, at least 0.3% carbon removal rate ensures good slag foaming. However, this is a figure which is obtained from some particular operation. Now, the next is scrap preheating. Now, as you are aware, a scrap which is charged at 25 degrees Celsius and a scrap if it is charged with temperature greater than 25 degrees Celsius. If you charge a scrap with greater than 25 degrees Celsius, that means preheated scrap, you are adding additional amount of energy along with the preheated scrap. So, naturally, if a scrap is being preheated, the electrical consumption will be low, meltdown period will be lower, electrode consumption will also be lower because now you have reduced the meltdown period, and accordingly the associated tap to tap time interval will also be low, and electrical power consumption will also be low since you are adding some amount of energy into the bath. The preheated scrap is a very important process technological operation in the electric arc furnace. The scrap is being heated by recovering the waste heat from the exit gases of the electric arc furnace. Now, imagine, suppose if I take preheat temperature, here I take preheat temperature and here I take energy introduced by preheating, in kilowatt hour per ton. Now, the very simple I can calculate it, that is the energy is m Cp into delta T. M I take for example 1000 kg, the Cp of steel I can take for example 0.162 kilocalorie per kg degree Celsius, and now if I calculate for example my preheat temperature is 150 degrees Celsius, then I will be adding around 23.55 kilowatt hour per ton of energy into the bath. If I heat up to 260 degrees Celsius, I will be adding around 44 kilowatt hour per ton of energy. If I heat up to 370 degrees Celsius, I will be adding around 65 kilowatt hour per ton. and if I heat up to 540 degrees Celsius, I will be adding around 97 kilowatt hour per ton of energy. Naturally, more is the amount of which is there with the preheated scrap, more amount of energy will be introduced. So, less amount of energy I will be required from electricity. So, obvious advantages of preheating scrap is though it is obvious, but still to complete the lecture I will like to write down the advantages. Increased productivity. I mean, these advantages you can derive from yourself by imagining that now you are introducing additional amount of energy. So, this additional amount of energy can melt more amount of scrap, then per unit of electrical power consumption you will get more productivity, more amount of metal can be melted. Second advantage is that reduced electrode and refractory consumption. Now, this advantage number 2, reduced electrode and refractory consumption, they are the indirect advantages, because what you are doing, you are decreasing the meltdown period because you have added certain amount of extra energy by preheating the scrap. So, if you add extra amount of energy, you are decreasing the meltdown period. If you decrease the meltdown period, the total tap to tap time will also be decreasing. Less time will be used by the electrode for heating. Of course, the electrode consumption will be lower because now the time is less. Now, for a heat, a particular heat is for less time in the electric arc furnace. So, obviously, refractory consumption will also decrease. Now, the question comes, how to heat this amount of scrap? It is very easy to calculate. Say on the board or or in the classroom, I can always take a temperature equal to 600 degrees Celsius or 800 degree preheated scrap temperature, and I can calculate that amount of energy and claim that aha, so much amount of energy is there, and hence I will be able to save the electricity. But the question comes, the extra investment. As I have said earlier, a technology requires ROI, return on investment, as well as payback period. Payback period should be low and ROI, return on investment, should be high. If you invest 100 rupees, your investment should be, or profit should be more than 100 rupees at least. So, what is required at this point of time or at this point to understand a development of technology in order to preheat the scrap? So, here if you closely observe electric arc furnace, you will note, and as I have also drawn an energy balance diagram for electric arc furnace, there I have shown that 20% of the energy is carried away by the waste gases. Remember, the waste gases temperature is around 13 to 1400 degrees Celsius. So, a technological person will think, why not to use this waste energy and develop a method for preheating. It is this particular idea that has led to the use of waste heat from the exit gases and to recover it by preheating the scrap and charging that preheated scrap in the electric arc furnace. Now, there are several technologies are available, several ways are available. Now, here again I will like to tell you that an efficient and economical technology is to be developed utilizing the heat of waste gases. I will show you two such technologies. Now, for example, this is a technology which is being developed for heating the scrap. Now, here this is the electric furnace, this is the electric arc furnace, this is the basket containing the charge, this is basket containing scrap, this blue line, they are the waste gas. This is of course hood. So, here the waste gases to bag house, waste gas to bag house. Now, say a portion of the waste gas is diverted to this particular loop and it rather enters into the basket. In that residence time in which the scrap is in contact with the flowing waste gas, the scrap will be heated up and the rest amount of gas is discharged into the bag house. Now, here the waste gases may be entering around 800 to 900 degrees Celsius. The waste gases which discharge to bag house is of the order of 200 degrees Celsius. The scrap gets heated up to a temperature of 300 to 450 degrees Celsius. Now, remember, this method is a sort of discontinuous one. That means, every time you have to stop the process, you have to take the bucket out, take it to the electric arc furnace and charge the preheated scrap into the electric arc furnace, again bring the bucket and do repeatedly that process. So, this is a discontinuous type of preheated scrap arrangement, but even then this has worked and this is working in some of the industry. Now, by this energy consumption will be reduced by a figure of 40 to 60 kilowatt hour per ton, and as regards the electrode consumption, that also be reduced, refractory consumption will also be reduced and tape to tape time will also be reduced. Now, to quote the figure, because that will vary from plant to plant. So, what I will like to tell you is that because you are putting an extra amount of energy, so it is obvious the power consumption will be low, tape to tape time will also be low, refractory consumption will also be low. Now, another development for scrap preheating which is also being working in some of the plant is a continuous development. So, this development has been developed by Cone Steel. Here this is an oxygen injection. This is, you can call as a scrap preheater, a scrap preheating arrangement, scrap preheating arrangement. These are the gases. This is hot metal, this is foamy slag, and here the best gases directly from the electric arc furnace, they are introduced into the scrap preheating system. Now, here somewhere here this is a connecting car. This is a connecting car. Scrap is going in this direction. Somewhere 25 degrees Celsius gets heated up and then it is charged into the melt. It's a continuous process. This is the waste gas. This is a waste gas. Waste gas and the scrap, they are traveling counter current. Very effective mechanism of heat transfer from the heat of the waste gas to the flowing or to the moving scrap. So, this is a sort of a continuous system for preheating of the scrap. Now, it looks very easy, but there are several complications or several intricacies are involved. One of the main intricacy is that you have to connect the electric arc furnace with the scrap preheating arrangement. This is one, and second, you have to optimize the length of this scrap preheating, that is this and this, such that the desired temperature of scrap could be attained, because the gases are moving continuously and scrap is also moving continuously. So, it is the residence time of the waste gas in the preheated section that will decide the temperature to which the scrap could be preheated. So, higher residence time, larger temperature, lower residence time, smaller temperature. But however, these are to be optimized, and the what is available is that the maximum preheating temperature could be attained by this around 300 to 350 degree Celsius. So, that is what the preheating scrap and the technology associated with it. Again, once again I will like to repeat that this preheating scrap technology has to be developed. It has to be developed keeping in view the parameters that are particular to a particular plant. It is not there that a technology which works in a X steel plant, the same technology will work in the Y steel plant. It may work, it may not work. So, that is about the process operating technology. The next development is usage of chemical energy. Usage of chemical energy. Now, uses of chemical energy, there are various ways in which this is being done. One is a oxidation reaction. Another post combustion. Third, oxyfuel burner. Oxyfuel burner, and fourth is carbon injection. Now, all these technologies, they require oxygen in order to derive the chemical energy, because chemical energy means what? You carry out a chemical reaction, and that chemical reaction must be exothermic in nature. When the reaction is exothermic, the amount of heat will be available to you. So, all these different facets of chemical energy, they require a system for oxygen injection. System for oxygen injection. Now, let us see what are the requirements. First, take say oxidation reaction. Oxidation reactions. Now, oxidation reactions, for example, iron gets oxidized, carbon, silicon and manganese gets oxidized. Silicon and manganese, they are low in quantity, iron and carbon are there. So, it is oxidation of iron and carbon, both are exothermic reaction and both provides energy to the bath. That means, the iron plus half O2, it gives you FeO, and the heat content by oxidation of iron, that will be 6 kilowatt hour per meter cube of oxygen. That much amount of heat will be available. If I allow carbon to proceed, say carbon oxidation, that is CO, then heat content will be 3.5 kilowatt hour per meter cube oxygen. You may be tempted to carry out iron oxidation because of the heat, but well, it is a loss. So, normally you do not allow iron oxidation to proceed. You allow carbon oxidation to proceed, so that the energy is introduced into the bath. Now, for carbon oxidation to proceed, you require a carbon content at least greater than 0.3% or 0.4% of carbon. Below that, iron oxidation will continue, and any amount of energy you will be introducing by oxidation of iron, it may be compensated by the loss of productivity. So, there is no point in allowing oxidation of iron. So, in order to obtain chemical energy by oxidation reaction, it is the carbon reaction that must be preferentially allowed to occur by having a carbon content at least greater than 0.3 to 0.4% carbon. So, therefore, in such cases where this requirement is not met, that is carbon content of the bath is less than 0.3%, then an additional carbon injection facility has to be developed if energy should be derived from oxidation reaction. So, remember, additional carbon injection facility is required. Now, for carbon reaction to proceed, where carbon is in the bath, how the reaction will proceed? You have to allow oxygen to penetrate deep into the bath. That means the condition for carbon oxidation to proceed is deep penetration of oxygen in the bath. That means high velocity. That means you require a sort of supersonic jet. You require a sort of supersonic jet. Otherwise, it will not work. Now, let us see another post combustion. As we have seen in case of BOF steel making, it involves the oxidation of carbon monoxide or hydrogen if they are present in the exit gases in the freeboard of the furnace, so that the heat which is created in the freeboard can be utilized for heating the scrap or slag or metal or whatever the case may be. So, the post combustion reaction are CO plus half O2, that is equal to CO2, and H2 plus half O2, that is equal to H2O. Now, for both these cases or for both the reaction to occur, CO and hydrogen should be available. Now, CO is produced first by reaction between FeO plus C or carbon plus O. These are the source of production of carbon monoxide. Then partially combusted hydrocarbons entering with the scrap. These are the say 2 or 3 sources for carbon monoxide generation. Now, hydrogen can be generated by the dissociation of the steam or the water vapor or the moisture that is present in the scrap. Now, CO and hydrogen they can be available at the free space of the electric arc furnace. That means above the slag, there CO and hydrogen would be available, but carbon monoxide it may also be available in the slag. So, that means the post combustion of carbon monoxide and hydrogen, it can occur either at the freeboard or within the slag. So, typically 20 to 30% combustion or post combustion is attained in slag, 80% is attained in the freeboard. Now, for post combustion to occur, what is required? Your oxygen injection system should inject oxygen at a low speed. Why at a low speed? Because oxygen should distribute well with the exit gases. Oxygen should be there where carbon monoxide is there. If you inject at a higher speed, then oxygen may go unreacted and your job is not being done. So, the requirement for post combustion is just opposite to that of oxidation reaction. That means now what you require? You require inject oxygen at low speed. If you want to utilize the oxygen completely, then oxygen should disperse well in the freeboard or disperse well in the slag if post combustion is carried out in the slag. So, the next is oxyfuel burner. An oxyfuel burner uses natural gas or oil together with pure oxygen to produce high flame temperature. So, here the requirement of oxygen is different. That means, oxygen should mix with the natural gas produces a flame, and that is being used in electric arc furnace. Now, the whole objective of using oxyfuel burner is in the meltdown period. After meltdown period, you do not require oxyfuel burner. In the meltdown period, in order to accelerate the rate of heating, you supply an additional amount of energy through the flame. There are hard scrap is there, then flame is directed to the scrap, it cuts down the scrap and it melts, so the melting is fast. Now, you see now the requirement for oxyfuel burner is different than your post combustion and oxidation reaction. You also do not require oxygen along with the fuel all the time, you just require in the meltdown period and then you want to stop it. So, this is what the oxyfuel burner requirement is. Now, typically industrial practice wants around 0.133 megawatt of burner rating. Should be supplied per ton of EAF capacity. Now, there are several other estimates. For example, somebody claims that around 32 kilowatt hour per ton of burner power is required in say high powered electric arc furnaces, where around 50 to 200 kilowatt hour per ton of burner power is required in order to eliminate the cold spots during the heating. Cold spot means where the electric arc is unable to reach. Now, the fourth is the carbon injection. It is very simple. You require a pipe to inject the carbon at the time when it is required. You know, the carbon injection may not be required all the time during the heat. You start from charging the scrap and then tapping around 2 hours. You do not require all the time all the functions. Say you do not require all the time to inject oxygen at a supersonic speed. You do not require oxygen all the time to inject at a low speed. You do not require oxyfuel burner all the time. You do not require carbon injection all the time. So, that means you have to have a burner which can do all the functions simultaneously without plugging the holes, because if you have the burner, you will be installing it in the furnace, and at different point of time different functions are to be done by that burner. So, the location of burner is very important. So, location of burner you can have either in the side wall or slag door. Side wall burners are the fixed mounting type of burner, and this slag door burner, you just take a submersible lance, go through the door and inject it and again take it out. So, the removal and injection is easier for a slag door, but whereas when the burners is mounted fixed on the side wall, then a burner is required where all the 4 requirements of oxygen can be met. So, typically a burner that rather works in a burner mode as well as oxygen injection mode throughout the melt cycle. Burner mode means you are using oxyfuel burner or you are injecting fuel. Once the meltdown period is over, then you go in the oxygen injection mode depending on the requirement of oxygen. So, now to summarize, say efficient use of oxygen require what? Efficient use of oxygen, it requires to have a burner which can work in hold mode. Which can work in hold mode. I am listing now the requirement of a burner which is to be designed to carry out all the functions simultaneously when it is mounted fixed on the side wall. First thing is that burner should be able to work in hold mode. That means what? The holes should not plug, holes should not plug, that is important. Second, in burner mode, that means I should be able to inject natural gas plus oxygen to create a flame during the meltdown period. Third, in soft launching mode, in soft launching mode. In soft launching mode means if I want to carry out post combustion, as I have said, low speed, so this will be when I require post combustion. Fourth, in supersonic launching mode, in supersonic launching mode, and that is when I want to carry out carbon oxidation, because then the jet should be penetrating into the bath, so I require a high velocity. A burner should also be able to work in carbon injection mode, in carbon injection mode, and that is when I require foaming slag, when I require a foaming slag. That is what I mean to say from here, that I require a singular device, not 5 devices. I require a singular device which can do all my functions, and at the same time the function which is not being performed and the hole which is being provided for that function, it should not be plugging. That is the requirement. So, such innovative design has been developed by a company called Preheating. They developed a design which can work in all the different modes depending on the time which is required. However, the design for this burner is not available because it is a proprietary item, but in summarizing I can say that these burners, they are installed on the side wall of the electric arc furnace, and these Preheating burners, they are working in several electric arc furnaces satisfactorily, and the whole idea of these burners is that they can inject in the mode in which during the operation an electric arc furnace requires. As I foresee, this particular injection system must have a combustion burner where oxygen and natural gas is burned, a flame is being introduced, and depending on the requirement the natural gas can be taken off, or if you want to inject a carbon injection, then the carbon injection pipe can be easily inserted, and so on and so forth. Not more than this design is available in the literature. But what is being done in this particular burner is that they employ the concept of CoJet technology. They employ a concept of CoJet technology. So, principle of CoJet technology, CoJet technology. Now, a cojet means a jet of oxygen is coming from a nozzle at a very high speed, and also it is surrounded by a flame. So, now let me illustrate what is meant by a cojet. Now, before that, let us see how the jet issues from a Laval nozzle, or how it looks when it is issued from the Laval nozzle. What I have shown is a profile of a jet issued from Laval nozzle at Mach 2. Mach 2 is, that means twice the velocity of sound, and velocity of sound of oxygen is around 329 meter per second at 298 Kelvin. So, in this diagram, this is a Laval nozzle, this is a Laval nozzle, and this is the free jet. This is the free jet. Now, this free jet is characterized by the density of surrounding divided by density of jet. That means, the behavior of the free jet is decided by the ratio of the densities of surrounding as well as jet. That means, a jet issuing from the nozzle, it spreads into the surrounding, and the rate of spreading depends upon what is the density of the surrounding. Typically, a supersonic jet, because when you say m is equal to 2, it is a supersonic jet. Its velocity of jet is more than velocity of sound. A supersonic jet is characterized by this, is called the potential core. This is called potential core. From here to here, this is called supersonic core. This is called supersonic core, and then this is the subsonic region. This is the subsonic region. So, I am giving here a relative behavior when the ratio of density of surrounding to density of jet is changes. For example, if this ratio is equal to 1, this is my basis of comparison, then this will be the length of potential core. From here to here is the length of the supersonic core. In the potential core, whatever velocity at the exit, that will be maintained throughout the potential core. In the supersonic core, the end point of the supersonic core will be where in the jet the velocity is attained to the sonic velocity. So, in fact, supersonic core will extend from here to here. This is the length of the total length of the supersonic core. Beyond this, there is a subsonic region. Now, if the ratio is equal to 1, then I have shown here whatever the length is, potential core is this, length of supersonic core beyond potential core is from here to here, and total length of supersonic core varies from here to here. Now, suppose if the ratio is less than 1, density of surrounding is less than the density of the jet. Jet is denser, so jet will be able to diffuse much higher in the surrounding as compared to when its density ratio is equal to 1. So, accordingly, if this is my exit of the nozzle, so you see this is the length of the potential core, this is the potential core length, and this is the supersonic core beyond potential core, and this total you can call as a supersonic core. So, the length of potential core as well as length of supersonic core, they are larger as compared to when the exit ratio is equal to 1. That means, if my surrounding is lighter than the jet, then the rate of spreading of the jet in the surrounding is delayed. That means, rate of spreading is low. So, on account of which the exit velocity of the gas is maintained over a longer distance as compared to when the ratio is equal to 1. Now, let us see what happens. So, imagine a jet of oxygen is being issued through a nozzle, and if the jet is surrounded by a flame, what will happen? What is the surrounding of the jet? The surrounding of the jet is of very low density. The density ratio is far less than 1. What will happen? That will lead to a jet which will spread very, very little as the jet exits the nozzle. So, now if if I create a nozzle where in the center I allow oxygen to pass, in the annular space I let a natural gas to flow, I ignite the mixture. So, the jet from this nozzle, it discharges as the oxygen jet which is surrounded by a flame. As a result of the explanation which I have given you for rho s upon rho j is equal to less than 1, what will happen for that jet? That means the length of the jet or the potential core length of the jet will be much longer as compared to what I have shown in the density ratio less than 1. This is what I illustrated in the next figure. Now, in the next figure you see that this is a sort of oxygen jet. This oxygen is discharging, and this is a flame. Here a mixture of oxygen plus natural gas. So, if this oxygen jet is surrounded by a flame, the density of the surrounding is very much low. So, you see the length of potential core, not the supersonic core, length of potential core is very large or very high as compared to the other two previous cases. Since length of the potential core is great or large, then length of supersonic core will also be large. So, length of supersonic core will be, if I say somewhere here, this is the end of potential core and this will be your say supersonic core length beyond potential core. So, total length of the supersonic core is potential core plus supersonic core. So, that means if now I put my steel bath somewhere here, if I put my steel bath somewhere here, that means I hit the steel bath with this particular jet, then what will happen? The jet will penetrate deep into the bath. On account of that, I can carry out carbon oxidation. If I do not want this highly penetrating jet, I remove the natural gas. So, the jet will behave in a similar way as that in the previous cases. So, what I have illustrated from here, that a jet surrounded by a flame, it has a higher potential core, and such a high potential core penetrates deep into the bath and it can meet the requirement of oxidation reaction. So, now if I can show here, for example, this is the nozzle diameters. These are the say nozzle diameters. That means, I want to show now the potential core lengths. I want to show now potential core lengths of oxygen jet, with different shroud conditions, So, what you see from here, this is a jet which is discharged in a hot atmosphere. This is supersonic jet with oxygen shroud only. So, length of the potential core is somewhere at 20-25 or something. Now, here this is a coherent jet, as I explained just in the previous figure. This is a coherent jet, that is fuel plus oxygen shroud. So, you see the length of the potential core is very, very long as compared to when the jet is discharged only in the hot atmosphere. Now, again say this is a supersonic jet. This is a supersonic jet with no shroud, So, what is being illustrated over here is that a jet surrounded by the flame, that is called the CoJet. A CoJet has the capability of greater potential core, it will penetrate deep into the bath and it can do a job of carbon oxidation. So, these type of burners using CoJet injection have been used by the proxy air to perform all the functions simultaneously. Now, some of the advantages of CoJet is that a coherent jet or a CoJet is longer than a supersonic jet, because its ambient is a flame. These coherent jet injectors can be installed above the bath and or in the side wall of the furnace to carry out effective bath lancing. So, what is being important is that this type of coherent jet technology and its translation into the design of the burner have allowed to perform all the functions which I have listed, for example, oxidation reaction, post combustion, oxyfuel burner and carbon injection. Through this type of design of the burner, all the functions can be met simultaneously. Next is development is the use of charged material. Electric arc furnace started with the scrap. Today, all grades of steel are being produced by electric arc furnace. There are certain problems with the scrap, that means availability of scrap of high quality. So, in order to meet the high quality scrap when it is not available, then alternatively charged material are to be developed. Now, the reason for development of alternative charged material is one, to meet shortage of scrap, and to meet the demand of quality steel, What does it mean? That means scraps, they contain tramp elements, and as such it is very difficult to remove tramp elements. All the tramp elements enter into the steel. So, those quality of steel which require no tramp element, there you have to find a scrap with a low value of this tramp element, that is a very high quality scrap is required. Now, in order to combat these particular problem, alternative charged materials are developed. What are the alternative charged materials? Say, what are availables? One is pig iron, or you call, if it is in the vicinity of the blast furnace, the hot metal availability. Now, you know hot metal contains 4% carbon, silicon and so on. So, now the electric arc furnace must be able to refine if scrap is to be substituted by pig iron. Second alternative charged material is DRI, directly reduced iron. Directly reduced iron when it is produced from coal, or HBI, that is hot briquetted iron when it is produced from natural gas and then it is briquetted. Third is iron carbide, Fe3C. Use of pig iron, now the maximum is a limit. You can't use more than certain percentage of pig iron. Why? Traditionally electric arc furnace was developed to melt the scrap only. No refining was envisaged, if at all refining was envisaged, for a very little amount. Now, with the increasing content of pig iron, you increase the impurities also, the carbon, silicon, manganese and so on. So, now You have to refine it. So, if the refining time gets long, then your productivity will be affected. So, the maximum percentage of pig iron that can be tolerated is of the order of 30%, not more than 30% hot metal. It gives benefit in terms of productivity, tape to tape time and so on. Now, as regards the directly reduced iron, this particular aspect we will take tomorrow in our lecture.